Thank you very much. Thank you for having us and giving us the opportunity to talk about our research, which for me, I do at the University of Manchester, where I'm a PhD student supervised by Ben Stappers. And yes, as has been mentioned, I'm part of the working group, which is looking inside supernova remnants and also very high energy sources like Pulsar wind nebulae. And also we have some unidentified tera-electron volt sources that we are searching as well. So I will go through, I will jog everyone's memory of what these sources look like, and then I will talk about what an observation looks like, and then I will talk about the searching pipeline, and then I will give you some brief results. So yes, supernova remnants, there's two main types. The first on the left, you can see the shell type. This is a beautiful image that recently came out that was taken by ASCAP in Australia. This is a shell of radio emission that you can see when the shock front is expanding and sweeping up the interstellar medium. On the right, we have a composite type. So in the center of this shell, we have what is known as a plerion. So this is the compact central object is driving some high energy emission in the center. This is a very good indicator that there is some pulsar or maybe other manifestation of neutron star present. So a little bit more about pulsar wind nebulae. So on the left, I show a beautiful, well-known X-ray image of the Crab Nebula. You can see the termination shock from the pulsar wind that has been injected into the interstellar medium. And we also see this in radio as a flat spectrum radio source, and also in gamma rays. So the Crab Nebula is the brightest continuous source of gamma rays. And these gamma rays are detected by observatories like HESS, so the High Energy Stereoscopic System, which is in Namibia, I think. And we are looking at some sources that have been discovered by HESS at tera-electron volt wavelengths, because they do not have any, well, 15 of them are confirmed pulsar wind nebula based on the spectrum and other counterparts, but some have no multi-wavelength counterparts, so we don't know what they are. And it's a bit difficult to tell what they could be based alone from the spectra. So we'll be looking at some of these as well. So currently I just speak about pulsars and radio supernova remnants. So on the left, I show the full PP dot diagram. So on the bottom, the spin period of the pulsar, and then how fast it's slowing down on the left. And I draw your attention to the top left of the main bulk of the up here, the main bulk of the radio pulsar canonical population. And the yellow squares are ones where there are confirmed supernova remnant associations. So there are around 63 of these that are, if you look at the green catalogue, that are confirmed to be associated with these radio pulsars, radio supernova remnants. Sorry. Now, on the face of it, it seems like the work is done because if you take the beaming fraction, one estimate is 20%, this is the number of pulsar beams that should be crossing our line of sight based on orientation and stuff like this. Then this is roughly a ratio of 20%. So perhaps they have already been found, but there are lots of caveats to this. So, for example, recently over 200 candidates have been found in a number of recent surveys, which I've summarized 3 big ones here. And so these have not been searched in any targeted sense. They may have been caught up in a lot of large surveys, but these have not been, most of these will not have been targeted with using targeted searches. So there is room for growth here. A few science questions. So in no particular order, there are a few really interesting science questions that we hope to contribute towards answering. So the first is the very interesting problem of the galactic neutron star birth rate. So Michael Kramer and Evan Keen's paper from 2008 was a very good summary and investigation of this problem. And I present a table from this paper here. So these numbers are all number of neutron stars born per century in the galaxy for each different manifestation of neutron stars. And they are compared against these are all for different models, and they are compared against a value calculated from measuring an isotope of aluminium, which is only the only path to this isotope that we know about. And you can see that none, when combined, none are consistent with the core collapse supernova rate. So this could be for a number of reasons. Perhaps the errors are simply too small on these, and so they are not overlapping. The errors have been underestimated, perhaps. Or it could be more interesting, so perhaps an evolutionary solution. So it may be RATs and perhaps these dim X-ray pulsars, which are neutron stars that are very close to Earth, and we can see them in their thermal X-ray emission. Perhaps these could be related in some evolutionary path, and that would reduce the calculated birth rate, because the birth rate would only be correspond to the birth rate of the youngest of these objects. This is very interesting. Also, it is not only that 20% beaming fraction which is stopping us from seeing some of these pulsars. There are other things at play. So some pulsars can be kicked out of their supernova remnant because of an asymmetric core collapse. So this will bias against finding them inside shells. There could be some effect from the low luminosity from these pulsars, the intrinsic radioluminosity. We don't know where the cutoff at the lower end of this distribution is, so perhaps this could be affecting our results. And there are some subtleties with formation scenarios, so maybe there is a different amount of black holes that are produced compared with neutron stars, which are the next compact object up from black holes. And the dispersion effects, and there are other observational effects as well. Finally, the energetics and energy budgets of these young pulsars that we expect to find is interesting. We want to constrain how much of the pulsar wind is injected into the interstellar medium and how that translates to different wavelengths of emission. So I'll race through what a typical observation looks like. So Emma talked you through how we beamform. So Wei Chen's software Mosaic is how the beamformer generates these delay polynomials that you can use to form coherent beams. So far we have looked in 39 sources, and it usually looks like this. So we will usually tile out the full we'll do full coverage of the radio emission we see if it's a radio signal. And we are very fortunate because we can look in lots of different places in one go because we are using lots and lots of small beams. So you won't have seen it this scaling, but there is a recently discovered candidate that is just to the lower left. You can see it better in the discovery paper from the Glow-Star survey. And so we can also put some beams on there as well and do like a 2-in-1. But we can be more efficient this way. So the processing, Emma mentioned this. So this is a sort of schematic of what's going on inside the Crew Array processing building. So the FBFUs, which was developed here alongside with the APSUs cluster. This cluster forms the beams with the correlated beamformer, produces the data product, and then we will process those on the APSUs cluster. A lot of the instrumentation was done by Ewan Bauer and his group, and also Prajwell, and it is we use the BGFS file system for the software distribution, and it's all orchestrated by Kubernetes, which is open source. And so yes, the processing is all done in different Dockers, so you can run commands as you please, and there's lots of it's very useful to do it like this. They're bridged by the website, so users can log on onto the website, and we can, in one of these Dockers, just run pipelines as we please. Not necessarily as we please, not all the time. We're kind of crazy. So the first step is, for my working group and several others, we use the PSoup pipeline, so time domain acceleration searching. Then that produces a whole bunch of candidates, and so those candidates need to be sifted, whereby there are similar periods and similar DMs, maybe they're the same source. Then they are folded using Youngpeng's Pulsar X folding software. They are scored, and then we can view them in a candidate viewing program that we use CandyJar by Hubek. Very useful. So we have one new pulsar discovery so far out of the 39 sources. That was the one orange dot that was in Michael's plot of tracking discovery. So So on the right, this is our discovery plot. This is what we saw in Candy Jar the first time. So you can see some parameters here, but I have an ephemeris on the next slide, so I can show you that. But yeah, so these are a whole bunch of parameters, but the main things are, this is the time series. So we're showing 2 rotation phases and the time of the observation. So we see 2 nice straight lines. Same again in frequency per channel. And then this is stacked to show the pulse profile here. So we've been timing this pulsar, and I show 2 timing observations here. And just because this is interesting, there is some flux variability here. So on very short timescales, 30 seconds, 1 minute, we have little flares of, well, I say flares, we have increases in flux here. We don't think this is scintillation because this is a much shorter timescale, and it's like a singular event, really. So we don't think this is scintillation. We just perhaps intrinsic to the pulsar. So yes, here's the ephemeris we have. We think we have a good timing solution now. We need to confirm this with more TOAs, but we think we have a pulsar that has, well, we know the period very well. It's 300 milliseconds. Period derivative of 3.8 times 10 to the 14. So on the PP dot diagram, this is zoomed into the young pulsars. It's somewhere here. So this looks like if we take a picture of pulsars being born here, and then they slowly migrate to the lower right of the PP dot diagram. This is a somewhat aged young pulsar. And then we have the estimations of E dot and the magnetic field strength as well. Characteristic age is 125,000 years. So we found this in an observation of this candidate supernova remnant, which was first discovered in X-rays, actually, in UNO et al. 2006. From the column density, they found that this X-ray emission is roughly 5.5 kiloparsecs away. From our DM, from our pulsar, we think that this is 4.5-ish kiloparsecs. And this was also discovered in Glowstar as a radio source. So we can see a very faint shell here. So we think that these sources are all linked, that this is one source, and that the driver of this X-ray emission is the Pulsar wind nebula driven by our pulsar that we discovered. So yes. I'm out of time, but I will leave the summary up here, and I'm happy to take any questions. So thank you.
If you discover the pulsar in this supernova remnant candidate, does it not mean that this candidate becomes a confirmation?
Yes, so we will need, there are some caveats. So it could be, this is the extent of this candidate was 15 arc minutes in wide, so it's not small. So it could be an overlap. So we have to do other things like match the X-rays, and our timing solution we think it fits.
Distance estimate for the remnant or spectrometrics or
the radio is a bit harder. So if you want to apply a surface brightness and diameter estimation to get the distance, you can, but the errors on this are very large because even amongst like same remnants, there are lots of differences.
I mean, if you estimate the age of 125,000 years, this is already long for the lifetime of a supernova
remnant. Yes. So we think that because this is right on the plane, so this is at 22 longitude on the plane, perhaps the density of the medium can keep the remnant more suppressed, then it ages slower. You think. Lots of caveats to this.
Any other questions for James? So your pulsar is not quite young, maybe more of an adolescent. And having 2 adolescents at home, I know they can flare up. So I like the story. So did you zoom into these flares, and are they giant pulses? Because that's really interesting.
Yes, I've done some very preliminary work. It looks like these are more than one pulse, so they're not single giant pulses. But they are quite bright. They drive up the signal to noise in 10 minutes from 10 to 25. So they have quite a lot of signal to noise. And they happen very regularly. We've seen them out in 5 out of 6 of the timing observations we've done with Mid-Cap.
It would be really interesting to look at single pulse. You can see single pulses there.
Yes.
Yeah, this is a really naive question, but you showed that in your comparison of different neutrons or species, you showed that the rotating radio transients are actually the most common neutron star type in this table. Is that something that is like commonly accepted as the truth? Because Yes, or
Yeah, so this number is based on the number of pulsars that we have. So we think that rotating radio transients are more ubiquitous than pulsars, but yes, we think that there are more in the galaxy than there are pulsars, but that doesn't necessarily mean that there are a number of subtleties here. Yes, we think they are more ubiquitous. The key is that this number here is based off this well-constrained birth rate, because we know more pulsars than any other, so we know this number the best.
Yeah, just because it's so hard to detect, there are rats where you know 2 pulses or 1 pulse, right? So most surveys miss most of them, so you have to extrapolate backwards from a relatively poor detection rate, but. Any more questions? Yeah, Colin.
Have you checked for gamma ray emission from?
No, we haven't looked into that.
Or X-rays as well. This would be the kind of.
Well, I guess we were hoping for more discoveries and then do one proposal that we can look at multiple pulsars at once. We're just waiting maybe for some more sources.